We now present a demo for the project, Situational Knowledge on Demand. There are 4 essential modules for the proposed architecture of SKOD. In the data streaming module, we built a data streaming pipeline between different sources of data and the relational database. For production-ready deployment, we are running all our Docker containers in Kubernetes. We can see all the RESTful Kafka producers have completed their run. The streaming Kafka producers are alive and populating the RDBMS with tweets. After this, we run the Kafka consumer container. In the consumer program, Flask web app is running to consume the topics. If we connect to the address, we will see all the streaming tweets in raw JSON format. We then parse them into structured format and put them into Postgres as seen here. After processing, the feature extraction modules are used to analyze raw data and find interesting patterns specific to the user and the mission. From the video data to extract features, we focus on object detection as the initial extraction task. We use pre-trained YOLO v3 to detect objects and find the bounding boxes. The benefit of using YOLO is it is fast and can be applied to streaming data. We apply YOLO on the MIT video data and detect objects such as cars, bicycle, person, truck and others. JSON data tells us what objects are detected in each frame, what is the bounding box coordinates for each object, and what is the confidence score. For extracting features from text, we extract texts that are similar to user queries using topic modeling. LSA is a widely used technique for topic modeling. For the demo, we are analyzing only the tweets from Cambridge Police. After we run the LSI program, we can see for the query, tree down, all the tweets that discusses about a tree down incident is extracted. Same happens for other queries. We will visualize this to have a better understanding of the similarity metric. Here we show for the query, person with gun, the first 10 tweets that matches the query. Document 1 has a similarity score of 78% for this query, whereas document 8 has an 85% similarity to this query. Now, for a new query, Massachusetts Avenue, we can see LSI can identify different kind of tweets that discusses different incidents in Mass Ave, such as fight at 5th Street or assault in progress at 4th Street. Finally, we start describing all the building blocks of the indexing layer and the application layer. First, we have all Docker containers of the OTA framework. For instance, the graph database layer that stores the indexing in a resource-aware management system. Also, the Apache Kafka microservice for data streaming. We also observe the graph lookup, the indexer, and the authorization microservice. We developed the indexing layer using the OTA framework from the OTS Center at Purdue. We start describing our web app, which is a React and JavaScript web application. The first step is to connect to the indexing layer. The indexing layer is an OTA-compatible data store which includes the graph database. We can also add more streams or topics of data. This list contains the actions that you can perform on top of the web app, such as adding a user, clearing the cache, visualizing the video frames, and running graph analytics. User will be able to pass queries to this front end. For this example, we will limit the query to extract multimodal data that contains cars. The multimodal streams of data includes text and video. After the user has passed his query to front end, he can choose to consume the data. The Twitter data has geolocations in it, so we are going to show it in the leaflet map. The videos are shown as frames. This is the state of the web browser's cache. This cache contains all the text and video data. Data is passed through WebSockets in real time. This is a tweet object that was pulled from database based on user's query. We can see the JSON metadata of the user who posted the tweet. These are the video objects with resulted frames that contain the objects of interest. WebSocket connections allow us to provide real-time feeds of different types of data. We can see the frames for cars are extracted successfully for the RESTful data. User can also apply graph analytics on the retrieved data from the front end, such as clustering. Benefits of this feature includes identification of affected area during a disaster. Using our user profiling, we determine user's interest. For demo purpose, we identify that the user interest is modeled as similar kind of objects as their previous queries. User can choose to see the retrieved data which is not a direct result of their query. For the query that asked for cars, we can see the frames that contain bicycles are also extracted for the same user. All the components of SKOD framework can be found in our GitHub repository.